In earlier lectures, we discussed at length some ways in which charges are the sources of magnetic fields. Let's do a quick review of that, starting with the case of a single moving point charge. Recall that the Biot-Savart law for a single point charge tells us how to find the magnetic field vector B sub q at an observation location described by vector r. Recall too that a charge must be moving, must have a non-zero velocity vector v in order to be a magnetic field source. Now let's consider a different situation. Like before, we'll start with a single charge q which is moving with velocity vector v. However, this time at the location of the charge we have a magnetic field vector B. Now let me emphasize, the source of this B field is not charge Q. The source is elsewhere. That other source is producing a B field at the location of charge Q. And as a result, there is a magnetic force on Q described by this relation. Q times vector V cross vector B. Notice that a charge must be moving in order to experience a magnetic force on that same charge. The magnitude of that force is given by the product of the magnitudes of Q, V, and B times the sine of theta, the smaller angle between vectors V and B when you put them tail on tail. The direction of the magnetic force is given by the direction of V cross B times the sine of Q. So, for example, if Q is greater than 0, the magnetic force points in the direction of V cross B out of the page in this example. However, if Q is negative, the magnetic force points in the direction opposite to V cross B, into the page here, if Q is negative. Let's try this question for practice. What is the direction of the magnetic force on the electron? Pause this video and try to answer this on your own before you continue. We determine the direction of the magnetic force from the direction of V cross B times the sine of Q. Here, by the right-hand rule, V cross B is in the minus Z direction, into the page. Now, we note that Q is negative. The particle is an electron. So the direction of the magnetic force on the electron in this case is the direction of minus V cross B. That is out of the page. So the magnetic force is in the plus Z direction. Here's a special case of the magnetic force on a particle. The special conditions are the magnetic field is constant and perpendicular to the velocity, and the resulting magnetic force is the only force, the net force, on the particle. In this case, the particle moves in a circle with constant speed. We can use Newton's second law to relate the radius of the circle to the magnetic field along with the particle's mass, speed, and charge. Now only the component of the net force perpendicular to the particle's velocity is non-zero. That's equal to dp dt, the time derivative of the momentum perpendicular to the particle's motion by Newton's second law. Let r be the unknown circle radius and m the known particle mass. Then the magnitude of F net is just the magnitude of the magnetic force, the product of the magnitudes of Q, V, and B, since V and B are perpendicular. And that's equal to the magnitude of dp dt perpendicular, which is the mass m times the speed squared divided by r. We can solve this expression to find the result for the radius r. Let's now turn to the case involving collections of charged particles, currents. Recall the Biot-Savart law for a short wire of length delta L and conventional current I tells us how to find the magnetic field vector delta B at an observation location described by vector R. Now let's consider the different situation where there is a magnetic field vector B at the location of the short wire of length delta L. The wire has cross-sectional area A and carries a conventional current capital I. Let me emphasize that the current in the short wire is not the source of the B field. The source of B is elsewhere, and that other source is producing vector B at the location of the short wire. And as a result, a magnetic force is exerted on the short wire. Let's call that force vector delta F sub B. Now we know that a single charge in the wire's current contributes a force of vector V sub D, the drift velocity, cross vector B times the magnitude of the single charge. Now since all the moving charges in the short wire's current see the same B field and have the same drift velocity, the total magnetic force, delta F sub B, is equal to this force on a single moving charge times the number of mobile charges. And we know from an earlier lecture that the number of mobile charges in the short wire is just the density of mobile charge carriers, N, times the volume of the wire, A times delta L. Rearranging this a bit, we see that in the parentheses we have an expression for the conventional current I. And notice that we have the vector delta L, which always points in the same direction as the conventional current and has magnitude equal to the length of the short piece of wire, delta L. Now, the direction of delta F sub B is always in the same direction as the vector delta L cross vector delta B, because the conventional current I is always positive. Let's try this question. Two current carrying wires of length L run parallel to each other a distance d apart. If a current is passed through the wires as shown, what happens? Stop the video and take a moment to try to answer this question on your own before continuing. Let's determine the magnetic forces on each wire in turn. First, let's focus on the top wire. The top wire sees a magnetic field due to the current in the bottom wire. Let's call this field B2. Using the right-hand rule for the magnetic fields from currents in wires, we can see that B2 is out of the page at the location of the top wire. Now we apply the cross product right-hand rule, delta L cross B2 at the top wire. Delta L points to the right, and we see the magnetic force of wire 2 on wire 1 is down. Now let's look at the magnetic force on the bottom wire. The field on the bottom wire due to the top wire, which we'll call B1, we can find again from the right-hand rule for magnetic fields from currents in wires, and that tells us B1 is into the page at the location of wire 2. Now we apply the cross product right-hand rule, delta L cross B1, and we find the magnetic force of wire 1 on wire 2 is up. So bottom line, we see that the wires are attracted to one another. That's it for now. In our next lecture, we will discuss the concept of flux for both electric and magnetic fields.